Now we are going to do the problem set for BJT circuits. Okay, now the first problem: for circuit shown below, the voltage across collector to emitter is measured to be 10 volts. Okay, that is this. What is beta DC of the transistor? Now what do we know about beta DC? Beta DC is output current over the input current. So what is the output current? Is the collector current IC and IB. Go to your formula sheet and look for the formula for IB and IC. Now for this problem, let me give you IB equals, in this loop you have VBB as the source voltage. There are two voltage drops. One is across RB, the other voltage drop is between the base and the emitter. So VBE is there. How much is VBE? VBE is 0.7 volts and the loop closes there. So one voltage rise, two voltage drops, right? So this voltage drop plus this voltage drop is this voltage rise. So now VBB minus VRB minus VBE equals 0, and VRB is what? The current flowing in this branch is IB. So IB times RB is VRB, right? VRB equals IB times RB. Now if you want to find IB, VRB over RB we will take, right? So here in this, the formula goes like this: VBB minus VBE over RB, right? So for finding this IB, VBB minus VBE over RB we use, and this one is VBB is given to be 5 minus VBE is 0.7 always. The value of RB is 100 kilo. Kilo is 10 power 3, and this is 4.3 over 100, right? 4.3 over 100 times 10 power 3. So this is on the calculator. 4.3 over 100, 0.043, right? So this is 0.043 times 10 power negative 3. Now we cannot give answers with many zeros in electrical, so what we do, we just get the whole number. So if we move one place to the right, one negative power is going to add up. So 0.43 times 10 power minus 4, 4.3 times 10 power minus 5, 43 times 10 power minus 6. So we can write it in powers in multiples of 3, 10 power minus 6 amperes. So 43 microamperes. 43 microamperes. IB we found. Next is to find IC. IC equals in this loop. Okay, in this loop VCC minus VRC minus VCE equals 0. Okay, now this is IC will be VCC minus VCE over RC. So VCC is 18 volts. 18 minus VCE is 10 volts divided by value of RC is 1 kilo ohm. So 1 times 10 power 3. So 18 minus 10, 8, right? 8 times 10 power negative 3, because this 10 power positive 3 in the denominator becomes 10 power negative 3 in the numerator. So this is it. Now we can find beta DC. This is equal to IC over IB equals 8 times 10 power negative 3 over 43 times 10 power negative 6. These ones we don't have to punch in the calculator because they are in division, so the powers are going to subtract. So 10 power minus 3 minus 6, right? So it's going to become this is going to be in the calculator 8 over 43 you do. 8 over 43 equals 0.186. 0.186 times 10 power negative 3 plus 6, right? This is going to be 10 power positive 3. So you can say it is 1, 2, 3 places, and these 3 powers will go, and it's 186. So your beta value is 186. We have finished this problem. The next problem here, determine whether the transistor in the circuit is biased in cutoff, saturation or active region. For this again you have to calculate IB and IC and also VCE, because when the transistor is in cutoff, VCE is going to be equal to VCC. Alright, there will be some IC, some IB. When it is in saturation, VCE is going to be 0.2 volts, 0 to 0.2 volts. Now when the transistor is in active region, VCE is going to be more than 0.2 volts, and it is going to be less than, VCE is going to be less than VCC. How much? Up to 80% we can keep, okay, because 20% we can leave for room for the errors. 90% also it will go, 100% also it will be sometimes, but when it is up to 80% we can say the transistor is in the active region. Alright, now let's start calculation. Again we'll calculate IB. IB equals VBB minus VBE over RB. So VBB is 1.5 volts. 1.5 minus 0.7 over the value of RB is 10 kilo. 10 times 10 power 3. Okay, so on the calculator 1.5 minus 0.7, 0.8, right? 0.8 divided by 10 times 10 power 3 is here. So this becomes 0.08, right? 0.08 times 10 power positive 3. 0.08 times 10 power positive 3, because this 10 power positive 3 becomes 10 power negative 3, okay, in the numerator. 0.08. now 1, 2, 3 places when you move, it becomes 80 times 10 power minus 6. You cannot leave with 8 because that becomes 10 power minus 5, not acceptable. 80 times 10 power minus 6 ampere, 80 microamperes is possible. So we have for IB 80 microamperes, okay. Now since it's 80 microamperes, we can say that the transistor is not in cutoff, okay, some current is there, right? Now let's calculate IC. IC by formula it is VCC minus VCE over RC, right? But here we are given, in the previous problem we had VCE given, right? In the previous problem we had VCE given, but in here we have beta DC. Now beta is what? IC over IB. With the value of this we can calculate by cross multiplying that formula. It's beta DC times IB. Okay, wherever required you can use this formula also for IC. Okay, IC equals beta DC. So 250 times the value of IB 80 times 10 power negative 6 equals 250 times 8. 250 times 80 equals it is giving 20,000, right? 20,000 times 10 power negative 6 it's giving. Okay, let us write it. 20,000 times 10 power negative 6. Okay, now when the decimal point is here, right? When the decimal point moves left one position, one positive power is going to add up. So we cannot also give the number with many zeros, right? So we are going to bring this point 1 2 3 places to the left and cut 3 negative powers from here and write it as 20 times 10 power negative 3. Okay, so 20 milliamperes. So we have 20 milliamperes for IC. So this is also saying the transistor is not in cutoff. Still, we want to know how much is VCE to clearly say if it is in saturation or an active region. For saturation, VCE should be greater than 0.2. For saturation, VCE should be equal to 0.2, 0 to 0.2. But if it is greater than 0.2, it's an active region. So let us see here. Now VCE equals VCC minus voltage drop across this, which is IC times RC, right? So this is VRC, right? VRC is by Ohm's law, IC times RC. VCC is what? VCC is 8 volts given. 8 volts times the value of IC is 20 times 10 power negative 3 times 8 minus this one, 20 times 10 power minus 3 times RC value is 390. So this we have to do, right? So 20 times, keep this away. First 20 times 390 we shall do in the calculator. 20 times 390 equals 7800, and from this times 10 power minus 3 here, right? So from this 1 2 3 places to the left, 7.8. so this is same as, this is equal to 8 minus 7.8, which is equal to 0.2. what are we finding? VCE. So 0.2 volts. So if VCE is 0.2 volts, the transistor is in saturation, right? So we can say transistor in saturation. Alright, so this is it. Next, we are going to the next page. Now, in this problem, we have to repeat problem 2. I just put the problem 2 circuit here with VBB 1.5, RB 10 kilo ohm, RC 390 ohms, VCC 8 volts and beta DC 250. Now this problem is saying change RB to 1 mega ohm. So RB, now it's changed to 1 mega ohm. Now we are going to say again if the transistor is in cutoff or saturation or in active region. Again we have to find what? 3 things. IB we should find. We have to find IC and we have to find VCE. Now let's write the formula for IB, IC and VCE. IB is what? VBB minus VBE over RB. Alright, now for calculating IC, we can use the value of beta and we can get the thing, like we can get beta DC times IB. This gives the value of IC in this problem. VCE is what? VCC minus IC times RC. Now VBB 1.5 minus 0.7 over RB. Okay, now 1.5 minus 0.7 over the value of RB is 1 mega, 10 times 1 times 10 power 6. Okay, mega is this. So on the calculator 1.5, 0.8, right? 0.8, this is 0.8 times 10 power positive 6 comes to the numerator as negative 6. So negative 6 is what? Micro. 0.8 microamperes, right? 0.8 microamperes. The next is IC is beta DC times IB. So 250 times 250 times 0.8 times 10 power negative 6. This is in the calculator 250 times 0.8 equals 200, right? this is giving you 200 times 10 power negative 6. So this we can leave it 200 microamperes, we can leave it as it is. If you want to bring down this these two zeros to null, so 1 2 3 places 0.2 milliamperes we can write. So this is equal to 0.2 milliamperes, right? So 250, this is like 200. So I moved the decimal point 1 2 3 places to the left and I removed those zeros, and by moving it left each time I got rid of one negative power and 0.2 milliamperes. Now this is VCC minus IC times RC. With these two we cannot say if your transistor is in cutoff or in saturation or in active. Okay, the transistor characteristic is going to be in the active region. Now so VCC 8 minus IC 0.2 times 10 power negative 3 times RC is again 390. So 390 times 390 times 0.2 equals 78, right? 78 times 10 power minus 3. So this is 8 minus 78 times negative 3 equals what? 0.078, right? The point is here 1 2 3 places. If it goes, the negative 3 powers will go, which is same as 8 minus 0.078, right? From 8 volts only this much is getting off from there. So 8 minus 0.078 equals 7.92 volts, right? 7.92 volts, which is close to 8 volts, right? So we can say the transistor is in cutoff. Okay, transistor is in cutoff, it's close to VCC. Cutoff till when we can say 80% off. 80% off, 80 over 100 equals how much? 0.8 times 8 equals what? 6.4. Up to 6.4 volts we can say it's in cutoff. Okay, 6.4 is small voltage, but 7.92 for sure it is in cutoff. All right, so this is solved. And the next problem, I have tried to explain here certain things and I recorded it also, but then I thought I'll record it along with this. Okay, now with respect to this characteristics, okay, for different IBs we have different curves. Okay, so the region where as the VCE increases, IC increases, is called saturation region, right? So up to here it is saturation region. In every curve, see, the VCE is increasing and IC is increasing. So up to here. After that the curve is saturating, right? The curve is just getting constant. IC is not increasing. So this is not 1, but this is 0.2 volts, right? So up to from 0 to 0.2 this change is possible. So this is saturation region of the transistor. The next region of the transistor characteristics from here to here, which is 10 volts, which is the the x-axis point for the DC load line. Up to that it's active region. Beyond this point is breakdown region of the characteristics, breakdown region of the transistor. Now this line, which is joining from the maximum collector current, which is called IC saturation, to VCC, which is the supply voltage on the collector side, when we drop a line, that is the DC load line. Now Q point or the operating point is marked here, and the question is asking the collector characteristic curves and DC load line of a BJT bias circuit are shown here. Determine the collector saturation current, IC saturation, VCE cutoff, and Q point IB and IC also VCE. Okay, Q point is the operating point, quiescent point, which is going to say the transistor is operating at that point. Okay, so I drop a line perpendicular to the x-axis and say that is VCE Q point VCE, and drop a perpendicular to the y-axis and that I say ICQ. Now just approximately by looking at it, since there is no marking, seeming at the center between 20 and 30, so I'm saying it is 25 milliamperes, and the corresponding IB for the Q point, it's going to be at the center between, this is like here, right? So between 200 and 300 microamperes, I can say it is 250 microamperes. Okay, so Q point, part C, IBQ, ICQ and VCEQ. IBQ is 250 microamperes from the graph. ICQ is 25 milliamperes and VCEQ is 5 watt volts. Okay, for a faithful amplification, for the signal to be fully amplified, the transistor should be operating at the center of the DC load line. The center of the DC load line is going to be, when you look at VCE, it's going to be 50% of the supply voltage VCC. Okay, so a VCEQ should be VCC over 2 for the Q point to be at the center of the DC load line. All right, so that also have shown here. All right, next is, let us calculate the collector saturation. This is also not not by any calculation, just by looking at the graph. Okay, so what is the collector saturation current? Collector saturation current, we can say it is like the collector, the y-axis is marked at this. So exactly speaking, this is the first curve, right? First curve that is touching the DC load line, right? So when you drop a perpendicular to the y-axis like this, now in this case you cannot clearly say this is 45 in the middle and 1 milliampere more, 46 milliampere we can say. Okay, 46 milliampere you can say, but you can even say this is just like, you can even mark it as 50, 46 to 50, it's less than 5 milliampere difference. That is also not wrong. All right, because that is the point where we have the IC saturation, the DC load line hitting the y-axis, right? So we can say for the A subdivision, we can say IC saturation equals 50 milliamperes, or more precisely 46 milliamperes. Okay, next is B, question part B is VCE at cutoff, right? At cutoff is what? The point where it touches the x-axis, the DC load line touches the x-axis, so that is VCC. Okay, so VCE is equal to VCE cutoff equals 10 volts. All right, next question here. For the circuit shown below, what is the value of Vin? What value of Vin will bias the transistor in cutoff? Okay, will bias the transistor in cutoff region. And part B is, if for Vin equals 5 volts, transistor goes to saturation, what is the value of RB? Now let us consider first we shall consider for cutoff. VCE is going to be what? Supply voltage. At that time, Vin is going to be what? 0 volts. There is no current in here, so there is no IB. which means Vin is at 0 volts. So for the first question, we can say for the transistor to be in cutoff, Vin equals 0 volts. Okay, what other things also we can say, IB equals IC equals 0, also 0. And we can also say they are only asking for Vin, so this is the answer. A, Vin is 0 volts. That is the time the transistor is cut off. Now Vin is going to be 5 volts. Okay, now we have to calculate the value of RB. Let's come to it. With this value, what we can find is for that we have to get the value of IC. Okay, then we have to use the value of beta DC, and then we have to go for calculating the value of RB. All right, because for RB the formula is, for calculating this RB value, we need to have Vin minus VRB minus VBE is 0. So Vin minus VBE over IB is going to be RB, right? So for finding RB, the formula would be Vin minus VBE over IB, right? Now for finding IB, we need the value of beta DC and IC, right? IC equals beta DC times IB. IB equals IC over beta DC, right? IC over IB is, so we need the value of IC also. So let's go for calculating the value of IC. And it has said the transistor is going to be in saturation. So IC, this is B. IC saturation equals BCC minus BCE saturation over RC. Now we know approximation for VCE saturation, this is going to be 0.2 volts, right? So VCC is given to be 5 minus 0.2. The value of RC is 1 kilo ohm, so 10 power 3. So 4.8 times 10 power minus 3 amperes. So this is what, 4.8 milliamperes. Yeah, so 4.8 milliamperes we have for IC. Now we have this. So let us calculate IB. IB equals IC over beta DC, that is equal to 4.8 times 10 power minus 3 over the beta value is 150. On the calculator you can put it as 4.8 divided by 150 equals 0.032 milli or 32 micro. 0.032 times 10 power minus 3 amperes, or move it 3 places and add 3 negative powers and write it as 32 times 10 power minus 6 amperes, 32 micro amperes. Alright, next is now we can calculate. We have the value of IB. So we have these values. Vin is given to be 5 volts in the problem. In the problem he has given it to be 5 volts. So the value of RB equals Vin, which is 5 volts, minus VBE, which is 0.7 volts, over the value of IB, which is 32 microamperes. So Vin 5 minus 0.7 over 32 times 10 power negative 3. This is equal to 4.8 over 32. Okay, 4.8 over 32 equals 0.15. 0.15 times, this one will go to the numerator as positive 3. So now 1, 2, 3 times it will take away, when you move the point 3 times, right? So 3 negative powers with 3 positive powers will go. That becomes 150 ohms. 5 minus 0.7 over 32. 5 minus 0.7, sorry, this is like 4.8 I have taken, right? So 5, I have only cut 0.2, right? So no, 5 minus 0.7 is 4.3, all right? 4.3 over 32. 4.3 over 32 is 1.134 times 10 power minus 3, which is 134.38 ohms. Okay, so this is not 0.15, but it is 0.134. 134, okay, 134. So this becomes the exact answer is going to be 134.38 ohms. Okay, so 5 minus 0.7, I had considered it as 4.8, so I got 150, but it is 134.38 ohms. So we finished all the problems from problem set. Okay.